So hello guys. So welcome back to our channel. So this is the live we are going to solve the daily LeetCode problem. So this is LeetCode 1545. So find the kth bit in the nth bit string. So in this string we are going to generate some string on the based on the binary string. So after that we are going to return the kth bit in the nth string. So what if I told you that it is one of the most satisfying medium problems on LeetCode, a problem that trips up nearly every beginner can make solve in just 6 lines of code, and not just solve but solve elegantly by understanding a single beautiful pattern hidden inside the problem. So today we are cracking the LeetCode 1545. So find the kth bit in the nth binary string. So this is the problem masterclass in recursive thinking, and once you see the pattern you are never going to forget it. So I'm going to take you through the every single step, the problem statement, the examples, the intuition, the observations, and the algorithm. So every line of code will have full explanation of why it's written that way. So a complete dry run, complete complexity analysis, and common mistakes to avoid. So if you are new here, so welcome. So hit the subscribe because I post daily lead code videos and code forces and every problem solving videos there. And if you have been struggling with recursion, this video is going to be changed how you think about it. So let's move on to the problem statement. So this is the problem statement. So we are given two positive integers, that is n and k. So there is a sequence of binary strings labeled as S1, S2, S3, and so on. So they are defined like this. First it is 0 and it is 0, 1, 1 like that. So they have defined a formula for that. So S of I equals S of I minus 1 plus 1. After that, plus the reverse string of inversion means we have to convert 0 to 1 and 1 to 0 of the S of I minus 1 for every I greater than 1. So where this plus denotes the concatenation operator, and the reverse of x means we have to return the reversed string, and the invert of x inverts all the bits for in x, that is 0 changes to 1 and 1 changes to 2, 0. So let's break down the problem. So now before we go further, we need to fully understand what this construction rule is actually doing. So let's break it apart. So this S of I is made of three parts. So the first piece is S of I minus 1. So this is the previous string that is unchanged. The second part is this one, the single literal of a character. So after that, the third part, that is the reverse of inversion of the previous word or previous string. So the first operation is we have to invert the words. So for inverting means we have to flip every bit. Every 0 becomes 1 and every 1 becomes 0. So that's it. Like flipping a light switch on every single character. So for example, let me open Notepad. So here first we have to invert the values. For example, let me take 0, 1, 1. So if we have to invert this, that time 0 will become 1, 1 will become zeros. So it will become 100 like this. So the next operation is reversing. So reverse means we have to read the string in the backwards. So the first character becomes the last word and the last becomes first. So let us give 100 here. So if we reverse it, so this will be the string. So after that, they are building the string from S1 through S4 manually. So let's do it manually. So the first four strings. So this is the crucial. So do this yourself on paper while watching. So it will make everything click. So the S1 is going to 0 directly. So we will not change anything. So the S1 is always 0. So next is S2. The string 2, that is first S1, then 1, then reverse the character. First the previous string. So after that, then 1, and after that we have to reverse the inverse string. So first let us do some more operations before that. So inversion of 0 is 1. So after that, reverse of 1 is 1. So now we have to create the second string. First we have to use the previous string that is there. So 0. So after that the concatenation and 1 and 1. Okay, this one is for adding the middle value, that is 1. We have given here. So after that, and this one is nothing but we have to invert it and reverse it. So after inverting we have to reverse the value. So now we have found the S2, that is 0 1 1. So let me make it a string here. So now the S3. So for the S3, first we have to add the previous string, that is 0 1 1. So after adding the previous string, we have to do two operations, that is inversion and reversing. So for inversion, we have to first invert the previous character. So it will become 1 0 0. So that is 0 1 1 will become 1 0 0. So after that we have to reverse this 1 0 0. It will become 0 1 1. So now we have to add the middle value, that is 1. After that 0 1 1. So the reverse means it is 0 0 1 1 0 0 0 0 1. So it should be 0 0 1. So now let me add all of them. So 0 1 1 1 0 0 1. So this is the third string. So the next one is fourth string. So for the fourth string, we have to just add the previous string. First the previous string. After that we have to add 1 in between it. After that we have to invert it, and after that reverse it. So first we have to invert. So invert. If we invert this value, 0 will become 1, 1 will become 0, and 0 will become 1, 1 will become 0. So this is the value. So after inverting, we have to reverse the value. So we have to reverse this. So we have to reverse this value. So if we reverse this value, so we'll get 0 1 1 0 0 0 1. So we just need to add this value in the last place. So now we have to add the entire string. So for that 0 triple 1 0 0 1 1 for the middle character and the finalized inversion string. So this is the S4, that is fourth string. So let me write this. with the indexes value, so we can visualize the positions. I'll be using one based indexing since the problem is uses one based. So now let me remove this. So here first the string 1 value is 0. So the index is 1. So after that string 2. So the second string is 0, 1, 1. So 1, 2, 3. So the third string is 0, 1, 1, 1, 1, 0, 1, 1. After that another 1, the third digit. So after that invert it and reverse it. That time we will get 0, 0, 1. So now 1, 2, 3, 4, 5. So 7 digits. So the next one is string 4. So fourth string is 0, 1, 1, 1, 0, 0, 1. Another one. So 0, 1, 1, 0, 0, 1. So after that 0, 1, 1, 0, 0, 0, 1. So let me give the index values 4, 5, 6, 7, 8, 9. That is 10, 11, 12, 13, and 14. So let us give some space. 10, 11, 12, 13, 14. After that 15 here. So these are the index values. So now we have visual. So let's look at the example test cases from the problem. So as you can see here, the first one is the n value is 3. The k value is 1. So here the s value is 3 means we have to find the string 3. So the string 3 is 0, 1, 1, 0, 0, 1. So after that the k value. So they have given the k value is 1. So the first value, that is nothing but in the S3 they have given 1. So now we have to give the value, that is 0, the first digit. So 0, the output is 0. So after that the n value is 4. So that is nothing but this S4. So they have asked for the 11th character. So the 11th character is 1. So the output is 1. So now here's the thing, we are not going to build an actual string. So the string 50 has the length, that is 2 power 50 minus 1, that's the over a quadrillion characters. So we can't store that. So we need to be smarter. Okay, so they have given the value of 20 here. So that is more than values that if you are doing this multiple times. So now move on to the building of the questions. So this is the most important section in this video. So if you understand what I am about to say, the code will be right itself. So pay close attention. So let's look the pattern here. So as we can see, this is the first half and this is the second half. This one is added in the middle. So this first 7 characters is the first half and the another one is the second half. So first let us see the observation of this problem. So now we write first the S1 length is 1. The S2 length is 3. The S3 length is 7 and S4 length is 15. So as you can see, these are related to some equational problem. So I can say that this is nothing but the S of n is nothing but the 2 power n minus 1. So this is n. So 2 power 1 minus 1. So 2 minus 1 is 1. So if you see here, so the 2 power 2 is 4. So 4 minus 1 will become 3. After that, 2 power 3 is 8. So 8 minus 1 is 7. So after that, 2 power 4 is 16. So 16 minus 1 is 15. So this is the formula. So as you can see, if you want to find it, so this means there is always an exact central element. So the middle index can be seen as 2 power n minus 1. So for the S of 4, so let me give the value, that is 2 power n minus 1. So the n minus 1 is, the n is 4. So the n minus 1 is 4 minus 1, that is 2 power 3 is 8. So I can say 8 is the middle element. So if we want to found the middle element, we can use 2 power n minus 1. And one more thing, that always the middle element is 1. So the 8 is 1. So for here we have to use 2 power 2, that is 4. So 4 is the middle element. So 1 here, and after that 2 power 1 it is 2. So this is the middle element. For 0 S of 1 it will be 0. So this is not a coincidence. So it's baked into a construction rule. So remember, each thing is formed by sandwiching a literal 1 in the middle. So by the definition, the middle character of every S of n for the value, that is n is greater than or equals to 2, is always the middle element is 1. Because for S of 1 is the middle value is 0. So the middle position, I can say, for finding the middle element, I can say middle value is 2 power n minus 1. So for let's see the first half of this S of 4. So see here, the S of 3 and the S of 4 first half is both are identical. So we are constructing S4 by prepending S3 at the front. So the first half of S of n is exactly S of n minus 1. Okay. So the first half of S of n is S of n minus 1. Understood? So this means if the position k were looking for false in the first half, so that meaning the k is less than mid, we can just recurse into s minus 1 with the same position k. So we haven't changed anything, we are just working with the smallest thing. Because if it is less than the middle value, we don't need to do the inversion and recursion there. We just need to do s of n minus 1. So that will be a smallest thing. So the next one is the second half. So the second half is nothing but the mirrored value. So this is the trickiest part. So look at the second half. So here, as you can see, the 9 to 15. So this is the second half. So in this second half, if you look at the value of the S3, 0, 1, 1, 1, 0, 0, 1, and it is 0, 1, 1, 1 and 0, 0, 1. So the second half is not same as the S3. So let's compare them character by character. Position 9 versus position 7. So position 9 is 0, position 7 is 1. And position 10 versus position 6. So position 10 is 1 and position 6 is 0. And so on. So they are mirrored. So not just mirrored, they are also inverted. So the position 9 in SF is S of 4 is 0 and position 7 in S of 4 is 1. So the both are flipped. That means it is being inverted. And after that, position 6 in the S of 6 is 0 and position 10 is 1. So both are flipped. So 11 is 1 and 5 is 4, 5 is 0. So both of them are flipped. So this is exactly what we said the second half is reverse of, see here, so the second half is reverse of inversion of the previous value. So that is nothing but the first half, but reversed and inverted. So this is nothing but the mirror. So how do we find the mirror position? If k is in the second half, we have to know which position in the first half it corresponds to. So the distance of k from middle in the k minus mid, the position is the same distance to left of the middle. So I can write a formula that is I can mirror the value of k to, I can mirror the value of k by middle value minus k minus middle value. So if you calculate it, you will get the value that is nothing but 2 multiplied by, because there are 2 times of middle value is there. So 2 times of middle value minus the value of k. So after that, if you again compile it, you can get the value that is 2 power n minus k. So let's verify it. So for example, if I give n value is 4 and k value is 11, so that time we will get the middle value is 8. So the mirror k is 8. So here I'll change the value to it. Middle value is 8 and the k value is 11. So 11, so the middle value is 8. So that time, if you solve this problem, you will get, there is nothing but here 5. So 8 minus 5, 8, this is 3. So 8 minus 3 will be 5. So the position 5 is S4 of 0. So the position 11 is S4 of 1. So for finding that, as you can see, the both are opposite. So if k is in the second half, so we have to find the mirror in the first half and recurse to get a bit at the mirror k in the S of n minus 1, and we just have to flip it and reverse it. So let's see the algorithm for it. So now let's put all three observations together into a clean recursive algorithm. So every time we call this function, we are asking what's the k bit in the string n. So here's the exact steps. So first, the base case. So if n is equals to 1, as we know, the value is 0. So we can simply return 0. So now first we have to write the base case. So here n is 0. So I'll return the character 0. So this is the base case. After that, we have to calculate the value of mid. So as we know, we have already found the mid value by using the formula that is 2 power n minus 1. So instead of doing that, we can simply left shift it. So if you left shift the value by n minus 1, you will get the 2 power value. So 1 is nothing but 2 power 1. So 2 power 1 is multiplied by the value that is n minus 1. So now you get the value that is 2 power n minus 1. So this is the second step. So after that, we have to check if k is equals to mid, we can simply return the value 1, because the middle value is always 1. So if my k is equals to the value of mid, I can simply return. So this is the third step. If k is less than mid, we are in the first half. So that time we have to return the value that is n minus 1 of k, the same position but in a smaller string. So we can simply recurse the function. So we can simply use else if here. So else if, so my k value is less than the middle value, I can simply call the function. So return find kth bit of the value n minus 1 and k. So we'll simply check the first half. So we don't need to check the second half. So if all of the cases are failed, that means we have to go to the else case, the right side of the string. So else. So this is the main part. So if k is greater than mid, we are in the second half. So we have to compute the mirror of the value and we have to recurse it to get the mirrored bit and we have to flip it and return the result value. So that's the entire algorithm. There are 5 steps. So every time we call it. So first it is the base case and we are finding middle value, and if it is middle value we'll return 1. So if it is less than the value, less than the middle value, we'll first check the first half and return the value. If not, we have to check the right side. So this is the 5 steps. So notice something beautiful. We never built any string. We never store anything. We just navigate through the mathematical structure of the string using the logic. So this is the power of the recursion. So now let us see the fifth part. So in the else case, first we have to find the mirror value. So I'll name it mirror k. So the middle value will be subtracted from the k minus middle value. So that time we will get the mirrored value of k within the value. So after finding this mirror value, we have to store the character. So mirror bit, I name it as mirror bit. So after finding it, we just need to call the function that is find kth bit, that is n minus 1, and the value that is nothing but the mirrored k value. So mirror k. So we have found the character. So now we have to return the value. But one thing is here, that is we have to return. If it is 0, we have to flip it to 1. In 1, we have to flip it to 0. So now I am using ternary operator. So if my mirrored bit is 0, so that time I will return 1. If not, I will return the value of 0. So this is the function. So let us see the line one by one. So the return type is character, so not integer. So not string, it is nothing but a character. So because the answer is a single binary character, we have to just return either 0 or 1. So these inputs are n, which string is sequence, and k is the position we want. So we are giving in a one index, not 0 index. So why 1 index? Because that's what the problem specifies. So always pay attention to the indexing conversion of by 1 errors or any single most common bugs in the LeetCode solutions. So next, the second line. So that is, if my n is equals 0, we simply returns 0. Okay. So this is nothing but, so this is not 0, this is 1 here, because it starts from 1. They have given the constraints. So look at the constraints. It is 1 to 20. So the s of 1 is nothing but 0. So if my n is 1, we have to return the value of 0. So when n is equals to 1, we have s of 1, which is just string 0. So no matter what k is, and the problem guarantees k is valid. So the only character s of 1 is 0. So we return 0. So this is our recursion flow. Every recursion path eventually hit n value 1. So and stop there. So without this base case, the recursion would go forever. So always make sure your base case is correct and complete. So you might wonder, can k ever be anything other than 1 when n is 1? So according to the constraints they have given here, as you can see here, it is 1 is k less than or equals to 2 power n minus 1. So if the value of n is 1, so that time 2 power 1 is nothing but 2 and 2 minus 1 is 1. So if n is 1, the maximum value that k can hold is also 1. So yes, so k is 1. So it is the only valid case here. So the next one is we are computing the middle value. So here we compute by the formula, that is we are using the expression of 1 double less than and after that n minus 1. So this double less than simple is nothing but the left shift operator. So it is equivalent to 2 raised to the power of n minus 1. So it is bit shift, it is called as bit shifting. So it is faster than comparing the power method that is we have given here, and there is also a floating point issues are there. So we are using left shift here. So now let's verify that. For example, if we give the n is 4 and the middle value is 1, so 1 double less than 3 is nothing but 8. So s of 4 have the length of 15. So position 8 is exactly the center value. So the next one is the fourth line. If k is equals to the value of mid, we'll always return 1 because the middle character is always 1. So we are returning. So if k is equals 1 or mid, so we immediately return 1. So this is our second case. So we proved it in the observation section that the middle character of any s of n, that n is greater than or equal to 2 is always be 1. So because the construction rule is literally inserts 1 there. So after that the fifth line. So this is nothing but the left part of the function. So here first half of the s of n is exactly s minus 1. So unchanged. So we can just recurse with the value of n minus 1. So we don't need to check the entire string. We just have it, and after that we will calculate the value. So notice here, so k does not change. The first half is direct copy of the s of n minus 1. So the position 5 is s of 4. So the same character as the position of 5 in s3. So this is elegant recursion. We are not transforming anything. We are just asking the same question about the smallest thing. And since n decreases by 1 each time, we will eventually hit our base case. Because every time it will call, it will again recurse it. N minus 1 will eventually become 1 and it will hit the value of 0 here and stop the recursion. So the sixth one is the second half. So in this sixth line, we have seen this else case here. So in this else case, if we reach here, k is greater than mid value. So we are in the second half. We need to find the mirror position of that. So the distance from k to mid is k minus mid. So the mid position is same distance. So the left mid of the mid. So mirror k value is mid minus k minus mid. So for example, if we give any value, for example, n as 4 and k as 11, mid as 8. So the mirror k value is 8 and 11 minus 8. So 8 minus 11 minus 8 is 8 minus 3, that is 5. So the position 11 is mirrors to the position 5. So as we can see here, so it is nothing but the position 5, that is 0, and it is 11. So it will become 1. So we will give the value 1 here. So the mirrored position is 0. So after checking it, we are checking the mirrored bit. So after finding the mirrored bit, we are calculating it, and if it is changes, we are reversing it. So this is the character that we are storing. So we are recursing to find a bit position that is in n s of n minus 1. So mirror k is guaranteed to be in the first half. So meaning the mirror k is less than the mid. So when we recurse s of n minus 1, mirror k is a valid position. So after that, we have to flip it and return it. So finally, we flip the result. The second half, so that is nothing but we are reversing the first half and reverse the inversion. So every digit is flipped 0 becomes 1 and 1 becomes 0. So we use ternary operator here. So for the compactness, so if we mirrored bit is 0, so that time I'll return 1. If it is 1, I'll return 0. So all three are equivalent. So if we can do, if mirror bit is equals to, we can return 1, and else case we can return 0. So but I am, for compatibility, I am using ternary operator here. So let us run it and check all the test cases are passed or not. So I have given string here. So now we can run it. So the test cases are being passed. So the first one is n value is 3 and k value is 1. So and the second test case is n value is 4 and the k value is 11. So as you can see here, n value is 3, that is S3, and the 1 is 0. In here, as you can see, it is 4 and 11. So S4 and the 11th character is 1. So the output is 1. So we are finding it. So this is a stack based method because we are using recursion here. So the first we see the time complexity of it. So each recursive call has a constant amount of work, a comparison, a bit shift, maybe subtraction, and every call reduces n by exactly 1. So we make at most n recursive calls. So therefore, the time complexity is nothing but big O of n. So given that the utmost in 20 constraints, this is extremely the fastest in practice. So it can at most call only 20 function calls. So even the largest input, we can only do almost instantly. So after that, the space complexity. So in the space complexity, it is also big O of n. So because we are, due to the call stack, each recursive call occupies a stack frame. So we got most n values deep. So we can use O of n stack space. So let's see what is the common mistakes to avoid. So before we wrap up, let me call out the most common mistakes I see people makes on this problem. So there are things that turn a clean solution into a wrong answer. So first one is zero index with the one index. So the most of the people confuse with zero index and one index. So here it is one index because as you can see it is highlighted with 0 here and highlighted with 1 here as the 11th digit. As you can count, you will get it is as a one indexed. So the next mistake is using power method instead of bit shifting. So I am using in C++. So in C++, power returns a double value, not an integer value. So if I use power of 2 power n minus 1, I can produce floating point errors like 7.999 instead of 8. So always use bit shifting. It is exact, fast, and it is an integer. And the one more mistake is most of them forget to flip the value after finding this value. So some people write the mirror k value and they would actually find that, but instead of that they will forget that they have to flip the value. So one more thing, that is they have trying to build the entire string. So if you try to write the entire string, so never try to actually construct a string. So for n up to 20, so the string has 2 power 20 minus 1 characters. So it is nothing but over a million characters. So for n value is 50, it's a quadrillion. The problem can have n up to 20, which means 1048575 characters. You can build it for the given constraints, but it is a terrible approach and it is exponential time and space. So when the recursive solution is only big O of n. So let's bring it all together. So let us submit the solution and check it passes all the test cases. So it is being accepted. So as you can see here, it is in the most least runtime. That is nothing but 0 ms. So alright, let's bring it all together. Here's everything you learned today in one shot. The string S of n is built recursively. Each new string wraps the previous one with 1 in the middle and inverted the reverse on the right. So the length of the string is 2 power n minus 1 in the middle position. So and the middle position is always 1. So the first half of S of n is identical to the S of n minus 1. So the second half is inverted reverse of S of n minus 1. So if k is in the second half. So if it is in the second half, find the mirror question, recurse it and flip the result. And the algorithm runs in big O of n time complexity and space complexity with up to the n value of 1, 0 to 1 to 20. So this is the essential instant. So if this video helped you, please give it a like. It genuinely helps the channels. Subscribe so you won't miss the next one, and drop a comment below telling me which observation clicked you first, and was it the middle always being 1 or the mirror formula. So I love to